Let's explore the process of creating truth tables from Boolean expressions. This involves converting logical expressions into a systematic truth table format. This will allow us to analyze and understand the behavior of these expressions for all possible input combinations. Let's familiarize ourselves with the fundamental elements of Boolean expressions. The basic operators are and represented by a dot, or represented by a plus sign, and not represented by an apostrophe. Here are a few simple examples. A and B written as a dot B. A or B written as a plus B. And not A written as a apostrophe. Now let's understand how to structure a truth table. Typically, a truth table includes columns for each input variable, such as A and B, and a column for the output. The rows list all possible combinations of the input values. With the values 0 and 1 filled in for A and B, we need to determine the output for each combination. For an expression with n variables, you need 2 to the power of n rows to cover all possible combinations. Let's create a truth table for the simple and expression f equals A and B, or f equals a dot B. The table includes columns for A, B, and the output A and B. When A is 0 and B is 0, A and B is 0. When A is 0 and B is 1, A and B is 0. When A is 1 and B is 0, A and B is 0. When A is 1 and B is 1, A and B is 1. Remember, with the AND operator, the output is only 1 when both inputs are 1. Now let's consider the OR expression f equals A or B, or f equals a plus B. The table includes columns for A, B, and the output A or B. When A is 0 and B is 0, A or B is 0. When A is 0 and B is 1, A or B is 1. When A is 1 and B is 0, A or B is 1. When A is 1 and B is 1, A or B is 1. With the OR operator, the output is 1 if at least one of the inputs is 1. Let's tackle a more complex expression. F equals A and B, or not A and C, or f equals it B plus A apostrophe dot C. The table includes columns for A, B, C, not A and B, not A and C, and the final output f. We need to determine each intermediate value and the final output for all possible combinations of A, B, and C, which are 0 and 1. For the first row where A, B, and C are all 0, not A is 1, A and B is 0, not A and C is 0, and f is 0. The second row has A and B as 0 and C as 1, giving not A as 1, A and B as 0, not A and C as 1, and f is 1. Row 3 A is 0, B is 1, and C is 0, so not A is 1, A and B is 0, not A and C is 0, and f is 0. Row 4. A is 0, B is 1, and C is 1. Not A is 1, A and B is 0, not A and C is 1, making f 1. When A is 1, B is 0, and C is 0, not A is 0, A and B is 0, not A and C is 0, and f is 0. Next A is 1, B is 0, and C is 1. Not A is 0, A and B is 0, not A and C is 0, and f is 0. The seventh row, A is 1, B is 1, and C is 0. This gives not A is 0, A and B is 1, not A and C is 0, so f is 1. Finally, A is 1, B is 1, and C is 1. Not A is 0, A and B is 1, not A and C is 0, and f is 1. Here is a step-by-step process for creating truth tables. First, identify the variables in the expression, counting the number of unique variables. Next, create the input columns, listing all possible combinations of the input values. Remember that with n variables you have 2 to the power of n rows. Then, add intermediate columns to break down complex expressions into manageable parts. Finally, calculate the final output by evaluating the expression for each row, using the intermediate values. Let's recap the key points. Always remember that truth tables show all possible outputs for a given expression. Break down complex expressions into smaller, more manageable steps. Verify each calculation carefully to ensure accuracy. Also, keep in mind the formula that n variables equal 2 to the power of n rows, which is essential for determining the size of your truth table. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.